5 minutes ahead of schedule. Let's move on to our first talk of the day, which is given by Professor Andrew Briggs. So Andrew is the Professor of Nanomaterials at the University of Oxford and has been involved for many years in quantum technology and quantum physics. He has over 600 publications and has recently co-authored a new book, which is on the bookstall. It's this one here, The Penultimate Curiosity. So let me commend that to you for a Christmas present. And with that, I think I will hand over to Professor Andrew Briggs. Thank you.
This talk will essentially be in two parts. The first part will be rather technical, and it'll include some technical physics. So I'll try to be as gentle as I can with that so that everybody can follow through. But if the odd equation pops up, please bear with me. And then in the second part, I'll turn to think about the topic of the conference more generally, the relationship between physics and faith, and particularly how curiosity is relevant to both of them. And at the risk of violating the clear categories that Russell gave us earlier, I'll include a bit of a personal dimension in that story and also show you a bit of a movie that Roger Wagner and I made after we'd written the book, The Penultimate Curiosity. I suppose that we scientists basically think that there's a world out there that has a reality to it. And as scientists, we're seeking to give a description of that reality that corresponds to it. And in fact, the test of our scientific theories and models is the extent to which they accurately describe that reality and predict the future behavior of it. And that worked well until one of the great physics theories of the 20th century was developed, namely quantum theory, which sort of threw into question the whole understanding of what reality is. And as people used quantum theory to describe quantum states, a sharp controversy arose as to whether or not these were real. Two of the sort of leading advocates of, or the developers of quantum theory were Niels Bohr and Albert Einstein. Niels Bohr was convinced that the quantum state was simply a sort of calculation device which would enable you to predict the probabilities of different outcomes of an experimental measurement. Albert Einstein found that profoundly unsatisfactory. And he was passionate that there must be some reality there, albeit one that wasn't adequately described by quantum theory as he knew it. Next March, I'll be going to Chicago to speak at the 80th birthday celebrations of Sir Anthony Leggett. Tony Leggett is a very remarkable person. His first degree was at Oxford in classics, what is called greats at Oxford. It was only after his first degree that he started to learn quantum theory. He became good enough at it to win a Nobel Prize in the theory of the quantum theory of cold materials, but he never lost the rigor that he gained in philosophy through studying the classics. And he wrestled with this question of, is the quantum state a state of reality or not? And here's one of the papers that he wrote about it 12 years ago. He said, well, there are different possibilities. Quantum theory might be the complete truth, and it might describe an external reality. It might be the complete truth, but describes no external reality. Or it might actually not be the complete truth, and somewhere there might be a sort of discontinuity in theory between the quantum theory of the very small, which has been so exquisitely tested, and the behavior of us in our us-sized lives, which seems to be very, very different. And I love this. He said, personally, if I could be sure that there'll never be a modification of quantum mechanics, then I should grit my teeth and plump for option B. But you can tell from that he doesn't like it very much. And because he's a very, very good scientist, rather than just sitting around arguing about this, he developed a very rigorous test. Now, at this point, this becomes necessarily technical, because if we're going to test something rigorous, we have to be technically precise. So he defined what he called macro-realism as the conjunction of the following two beliefs, beliefs in a sort of philosophical sense of postulates that you hold to be true. The first one is that a system is always in one of its available states. So let's say it's a system that can be in two states, then at any time it's in one of them. And second, it's possible to determine the state of the system without altering its subsequent evolution. In fact, he later modified that to include its previous evolution too, so that it's time symmetric. And then if you let the value be either +1 or -1, you can rather easily show that if you make 3 successive measurements and take the correlations between those measurements, then the function f, all right, can never be negative. And you can work that out. You just try, well, supposing it starts off as +1, and then after that it's -1, and after that it's +1, you just sort of calculate that in your bath, and you see that you can never find a combination that's less than 0. It turned out to be extraordinarily difficult to implement this test. For a quarter of a century, nobody could see how to do it. And then I was coming to the end of running the UK national activity in quantum computing, and I'd taken 3 weeks at the Kavli Institute of Theoretical Physics in Santa Barbara to look out to sea, both metaphorically and literally, actually, and think what I was going to do next. And I had an idea as to how one might be able to test this theory. And so I devised an experiment which, when I came back, we were able to implement in the laboratory. I won't go into all the details because they're rather technical, but it basically involves impurity atoms of phosphorus in silicon. And it involves the state in question being the nuclear spin of the phosphorus impurity atom, and then you use the associated electron spin as a sort of ancilla for doing the measurements. And it's a technical experiment, so we had a sequence of microwave pulses that are represented at the top. And in the pictures in the bottom, the blue region and the red region each show the limits of the Leggett-Garg inequality in with two different assumptions. The blue one is, we know this is an imperfect experiment because we have finite temperature and finite magnetic field. Let's assume that the imperfections just average out, as we'd sort of expect. But then, because we are testing some fundamental concepts, we ought to consider the possibility that there's some unidentified mechanism whereby, as it were, all the uncertainties conspire to give us the worst possible case, and that's represented by the red there. I once was explaining this to Serge Haroche, who subsequently won a Nobel Prize, not because he talked to me, for other reasons. And we called the first one the moderate realist, and the second one the aggressive realist. He called it the neurotic realist. And you'll see that in the first experiment we did, the black is the actual data, the gray is the data corrected for known errors, and the curve is the predictions of quantum theory. And you'll see that here we violated the inequality for the moderate realist, but not for the neurotic realist. So then we thought how to do the experiment better, and we redid it, and we've now violated it both for the moderate and for the aggressive realist. And what that's saying is that, at least in this experiment, macro-realism, as defined by Tony Leggett, cannot be true. So there is no reality in this experiment in the very precise sense defined by Tony Leggett for this purpose. And I find it absolutely amazing that we can take a philosophical interpretation of an important theory in physics and actually say something about the that philosophical interpretation on the basis of experimental data that we can measure in the laboratory. We then did a more advanced test of this, and I don't know how best to explain this. Has any of you ever seen this con trick that you sometimes get con artists doing, where you have 3 cups and there's a ball under one of them, or a pea or something, and he says which one's it under, and you look and it's there, and he swizzles it around, and then you get so confident that you know where it is that you bet some money on it and lose all your money. And there's actually an Egyptian picture from several years before Christ, which seems as if this con trick has been going on for over 2 millennia. And it's a bit like that, but it's a quantum version of it. So we've got 3 boxes. We've got a ball in one of the boxes, and Alice swizzles them around, and then Bob is allowed to look in one of 2 boxes while Alice is out of the room. And if he sees, I'm trying to remember which way it is, it's that if he sees the ball in one of the boxes, then Alice wins, but if he doesn't see it, then he wins. Alice comes back, she's allowed to open, she can do some more swizzling, she can open box 3, and she can then choose whether or not to accept the wager for that round. And this is an example of what in quantum theory is called a pre-selection and a post-selection experiment. It was developed by Yakir Aharonov as what he called the 2-vector model of quantum theory. So you have one evolution of the quantum state going forward in time and another evolution of the quantum state going backwards in time. Anyway, the point is that you set the game up so that Alice, who's the younger and cleverer of the 2, believes in quantum theory and does not accept realism. And Bob, who's the older and less clever of the 2, is a classical physicist who does think that there's this objective reality. And we actually did this experiment, and I won't go into all the details except to say that we used nitrogen vacancy defects in diamond to do the experiment. And it's quite a technical experiment, so this just illustrates all the different signals that we've got going on and the different stages in the experiment. Without going through it all, I want you to get the sense this is real science going on. It's actually quite a hard experiment to do. And if we look at the results of it, we can ask some questions. Do Alice's observations depend on Bob's? Can she tell which box he looked in? Can she tell whether he looked at all? And can she win? And what we've got up here is Alice's measurements, first when Bob looked in box 1, M1, second when he looked in box 2, M2, and thirdly when he didn't look at all. And indeed, Alice cannot tell which of those was the case. That's rather important in this experiment. And then we ask, can she win? And these are experimental data. They've got real experimental uncertainties. And the key point is this 50% dotted line here. And if Alice can do better than 50%, then macro-realism does not hold in this experiment. We've ruled out macro-realism, and you can see that we've ruled it out by many standard deviations in the experiment. So I've gone very fast through that because I don't want you to get bogged down in the details. But I do want you to get this sense that this is another way, and it turns out to be a more sophisticated way of testing, of doing the Leggett-Garg test, which is a rigorous test. We violated it by 11.3 standard deviations if we assume that the errors are random. Even if we assume that the errors conspire by some mechanism that we haven't identified, we've still violated it by 7.8%. And we also showed that the measurement is non-invasive because you remember Alice couldn't tell whether or not Bob had had a look. So what we're doing in all this is we're taking an interpretation of reality, which would be a philosophically tenable one, and showing that at least in the experiments we're doing, that philosophical interpretation of reality is not tenable. Now I'm going to do one more thing, and then we'll sort of back off from these technical details. So if your head's spinning a bit at the minute, don't worry, it'll get easier as we go on. There's another problem in quantum theory, which is to do with the measurement of non-orthogonal states. And the best way to explain this in everyday terms is this. Supposing that you're responsible for analyzing a survey of a population, and you're allowed to click on one button on the screen, you know, on your web browser for each person. And you can either click on the button that says, "This is a male," or you can click on the button that says, "This person is over 21. So if, for example, you have a 10-year-old boy, it's easy. You click on the button that says, you know, this is a male. If it's a 50-year-old woman, it's easy. You click on the button that says, this person is over 21. But if it's a 40-year-old man, then you've got a puzzle. Which button should I click? Because I could equally click either of them. I could either click that this person's a male, or I could click this person's over 21. And there's no way of deciding which of those you should press, so it becomes a sort of random choice. Now, with orthogonal states in quantum theory, we have a rather similar problem. It's quantum, so it's never quite the same as the simple example that I've just given. And it means that if we have non-orthogonal states in quantum theory, then a single measurement can't tell us which of the two it is. And that's represented by this sort of schematic diagram here, you see. So here's one state, and there's another state. If I measure this, then it's clear it's that one. But here are two states, and if I make a measurement here, I could think it's that state or it's that one. And one of the ways that people have tried to get round this is by supposing that there are some underlying ontic states. For this purpose, ontic just means they're real. They've got some reality to them. And the question is, does the quantum state represent a distribution of underlying ontic states? And if you think that that's correct, this is labeled as a so-called epistemic description of quantum theory. And it's sometimes called a psi-epistemic description, where psi stands for the quantum state. Psi is a Greek letter that's often used for the wave function. And over the past few years, starting with this paper in 2012, there's been a remarkable series of theory papers saying that interpretation won't work. And a more recent paper than that one is this one by John Barrett, which was published 3 years ago. And the conclusion of this paper
In the book that Andrew and I wrote together, we traced these motivations as far back through history as we could go. And now we're going on a journey to explore some of the key places in the long and extraordinary story that we discovered. I can remember that in the 1990s, what people called the human revolution only happened when Homo sapiens migrated from Africa to Europe and started making paintings.
And what changed that was the discovery in the Blombos caves in South Africa of evidence that people were making symbolic markings 100,000 years ago.
I mean, in the newspapers they describe it as the first artist studio, which I love because they found these extraordinary abalone shells which were used for storing and actually mixing pigment.
Only last year in Indonesia they discovered evidence that when humans started to migrate from South Africa, one of the things they took with them was painting.
And the first European paintings were discovered just about the time we started writing this book.
Or at least thinking about it, yes.
Yeah, and that's where we're going now.
À la France!
Golf Papa Lima, I'm completing my run-up.
This journey will take us across the world and across time. It will begin in France with that discovery of a vast complex of prehistoric paintings. Paintings that the leader of the excavations is convinced were religiously motivated.
We know they have a religious motivation, first because people didn't live inside those caves.
But paintings which also show an astonishing attention to anatomical accuracy.
Doing it with such accuracy might have been vital because they were recreating them.
It was made perhaps 35,000 years ago, and it's an astonishing piece of work. The journey will take us on to a city on the coast of eastern Turkey.
I mean, the ruins are somewhere inland, so I'm not sure we'll see them. In 600 BC, Miletus was a coastal town, a wonderful centre for new thinking.
A city where, in the 6th century BC, a new idea of the divine coincided with a new kind of interest in the natural world. From there we'll follow the route by which one man brought this idea to 5th century Athens.
Plato said he was the first person to work out how the shadowing of the moon was related to the sun. Yeah, and he also said that the sun was not a god, but a fiery ball, which in 4th century Athens must have been a pretty controversial thing to say. Yeah, I think he was probably quite a courageous chap, actually.
And visit the places where it provoked opposition and sparked a whole new way of thinking about the gods and studying the world. We will follow the path of these ideas to Alexandria in Egypt. But what happened in this great multicultural city when the philosophical religion of the Greeks and the revealed religion of the Jews and Christians came into contact? Well, the answer was riots. But we will also see how in a newly discovered philosophical school, where Christians and pagans studied together, a Christian philosopher who insisted that nothing should get in the way of truth, anticipated one of Galileo's most famous observational experiments by almost exactly 1,000 years.
Two unequal weights dropped from a given height strike the ground at almost the same time.
Following this trail forward to the city of Pisa in the 16th century, we will discover how Galileo not only repeated that observation, but followed in that early Christian philosopher's footsteps in his conviction that pursuing truth as a Christian duty would reveal deep laws that govern the whole creation. Coming back to Oxford, we'll see how in the 17th century religiously motivated natural philosophers sparked what we now call the scientific revolution. And finally, travelling first to Scotland and then to Cambridge, we will see how a 19th century scientist wrote down 4 equations which showed that the whole universe was filled with the surge of electromagnetic waves.
Their description of the fundamental gearing between space and time led directly to Einstein's theories, but they also provide the basis for all the electronic technologies that shape the modern world. The world we live in today begins with these equations.
And we will see how for that 19th century scientist, the discovery of those four equations, which revealed the deep unity of fundamental aspects of the universe, was carried along. Human beings seem to reach out beyond the horizon of the visible world in order to try and make sense of it as a whole. You could describe it as ultimate curiosity. If then our curiosity about the world around us moves, as it were, in the slipstream of that ultimate curiosity, you could describe it as penultimate curiosity.
Where do we go from there? Well, over the past couple of years, I've been discussing where all this might next lead us with two friends and colleagues. This is Andrew Steen. He's a professor of physics at Oxford. He was responsible for the breakthrough that showed that quantum computing would be possible in practice. The breakthrough was known as fault-tolerant error correction. People had thought up till then that error correction would be impossible in quantum computing because of a theorem in quantum science called the no-cloning theorem. It says you can't photocopy quantum information, which is normally thought to be necessary for error correction. And Andrew came up with an absolutely brilliant way of getting round that problem, which completely transformed people's belief in the feasibility of quantum computing. And then this is Hans Halvorsen, who is a professor of philosophy at Princeton University. He's got an interesting background. He came from a Christian home that was a very strong Bible-believing Christian home. And as can sometimes happen in the USA, I hope it scarcely happens in the UK, felt that if you were a Christian, a member of his church, then science was not for you. And so he didn't go into study science as an undergraduate. He studied philosophy instead. But then he, because he's a remarkable, aptitude for science, he's made some of the key advances in the philosophy of quantum theory. He's for a long time wanted to get into the philosophy of religion. And so discussing these things together has sort of reflected something he's wanted to do for a long time. We're here discussing these ideas with Green Templeton College in the background, the Tower of the Winds there. Only after we'd taken this picture did Roger Wagner point out to me the similarity with the frontispiece of Galileo's discourses, where the attitudes of the heads are almost identical. So you've got here Aristotle and Ptolemy and Copernicus. Any similarity is entirely unintended, of course. And as we've thought about these things, we've come up with three themes, which I'd like to leave you with as the sort of conclusion and maybe a discussion starter. And the three themes that we've come up with, I beg your pardon, four, are first of all that God is a being to be known, not a hypothesis to be tested. If I'm wanting to engage with you in this room, I don't actually promote the most fruitful engagement by spending the entire time arguing about whether or not you exist. That's not a good way to develop a relationship. And this year's, the 2017 Templeton Prize went to a philosopher called Alvin Plantinga. And one of his great contributions was to establish philosophically, and I'm going to use the technical terms, that it's okay to have God as a basic. In other words, you can start with that and move on from it, rather as Euclidean geometry started with axioms and moved on from them. The second one is that we set a high bar on what constitutes a good argument. And there are quite a lot of arguments, for example, arguments for the existence of God. And it's very hard to object to an argument when you agree with the conclusion. But actually, I think we should have the courage to do that, because we don't want faith to rest on shaky ground, on sands that will wash away when the intellectual storms of harder questions come. The third one is that uncertainty is okay. We can live with uncertainty. It's only, funny enough, it's people who worry about science who have them. Every businessman, every successful businessman is successful because they repeatedly take good decisions in the light of incomplete information. That's how to succeed in business. And in science, science thrives by, those of us who are doing science research, finding the boundaries of knowledge, finding the places where knowledge is a bit uncertain, and investigating it, and being willing to change our minds in the light of new evidence. If necessary, changing our minds about things that we thought were absolutely integral to the way we do science. But this needs to be nuanced. So just because science has uncertainty, that doesn't mean that science isn't confident about anything. We can be pretty confident about the phase diagrams of aluminium alloys. In fact, sufficiently confident, literally, to trust our lives to them every time we fly in an aeroplane. So to say that we live, uncertainty is okay, doesn't mean abandoning all confidence in everything. And this is one of the areas in which we can learn from science. You're going to stop me at 20 past. Which is the fourth point there, that we can open up the window that the natural world offers to us, and there are many areas in science, in faith, where we can learn from science, and one of them is this, that I started off by telling you about these unresolved questions about the nature of reality in quantum theory, and it's actually worse than I described. There is no consensus amongst my colleagues about what happens when you make a measurement of a quantum system. But that doesn't stop us developing quantum technologies. And we can sort of live with unresolved questions and still get on with it. And there are many questions in the life of the Christian faith which are unresolved. I could give you some, but Russell's standing up. But we can get on with it without diminishing our quest for the truth. Thanks.
Thank you very much indeed, Andrew. We've got plenty of time for questions. There's a roaming microphone. So, who would like to kick off questions? Rachel, could you?
Hi, Professor. By your words discussing about uncertainty, so what's your idea about uncertainty with faith? What's the relationship they have? And is that possible that uncertainty is the space for God that still can operate in the world?
What a wonderful question to start off with. Thank you very much indeed. And let me take your question in two parts. First of all, what is the realm of uncertainty in faith? Far be it from any of us to say that we know everything that there is to know about God. Maybe some people would claim that, I hope not. So, in the life of faith, we should be open to learning more, to understanding at deeper levels, as a continuous journey, and a very exciting one, and a lovely adventure. That journey is best carried out if there are some basic things that we can be confident about, and we are sure of. And I suppose I should nuance that by saying some of those may be choices that we've made. So there's an extent to which belief is a glorious combination of objective data and personal choices. Your second part of your question is this uncertainty, the space for God to operate on? And I think that is a terribly dangerous road to walk down, because you very quickly end up with what's often labeled as a God of the gaps view, which sort of says that God moves in the gaps in our knowledge. And that's a disaster in practice, and it's a disaster conceptually. It's a disaster in practice because those of us who are doing science are constantly trying to fill in gaps in our knowledge, and that would squeeze out the space for God to operate in. Actually, it would also diminish our motivation for doing science if we believe in God. It's a disaster conceptually because it suggests that God is only the God of the things that we don't understand. And the whole point of that text that Maxwell chose to put on the doors of the Cavendish is that what we're doing is as scientists, we're studying how God does do things. We're studying how God makes the world work. That gives a motivation for science. And if we find out, we don't say, oh, bother, that means God didn't do that bit. We say, hurrah, we've understood a bit more of how God works.
Would you, do you believe that God can only be known via the intellect?
Oh, no. Because otherwise, the quality of your relationship with God would depend on your promotion as a professor within Cambridge University. But I do believe that knowing God stands up to intellectual scrutiny.
Hi, I'm just trying to understand or try to visualize what reality actually means. So in one sense, I would like to ask, how do you actually define reality, and how do you contrast reality versus non-reality, or do you have some sort of analogy to help us understand these concepts better? Thank you.
That's about the hardest question you could ask. So let's try. I'd love to know what other people think, actually. Let me give you an extreme idea of non-reality. If you said, actually, there's no God at all, and all religion is just sort of construct of our minds, it's just what we invent ourselves, I think it would be hard to describe that as reality in a useful sense. So what is reality? Well, you may have sensed that for any particular investigation, we might need to have a very rigorous technical definition. Certainly that was true in Tony Leggett's work and in the subsequent work about psi-epistemic theories or maximally psi-epistemic interpretations. And so I think this is a question to wrestle with, actually. I think it's not a question to give a sort of neat, tidy answer to. But let me give you a little bit of a clue that before quantum theory, you might have thought that the moon is an objective reality, independent of whether or not we look at it. Not everybody would have thought that. There was a famous bishop, Bishop Berkeley, who thought that reality was something that came from God and depended on awareness, which led to this rather lovely pair of ditties. What was it? There was a young man who said, God must find it exceedingly odd to think that that tree continues to be when there's no one about in the quad. And this evoked the response, young man, your astonishment's odd. I am always about in the quad. And that's why that tree will continue to be, since observed by yours faithfully, God. So this was a pre-quantum debate. But the nature of the debate changed when quantum theory came along, and there's this famous question that Einstein put to Abraham Pace once when they were out for a walk. He said, do you think the moon is there when nobody looks? And So that's the sort of question about the nature of reality. And I think the new insights that we may be getting, I'm not sure about this, so I'd love to know what other people think. The title of the book that we've written is called It Keeps Me Seeking, and it's what it says on the tin. You know, we're discussing things in the book that we're still thinking about. That's why we want others to join in with this inquiry with us. It may be that reality is more relational than we'd previously supposed. And it may be that it's less helpful to think of God as being like the moon, who's there when nobody looks. And more helpful to think of reality, you know, your experience of my reality, of mine, of yours, as taking place in the context of a relationship. I'm not sure about that, and I'd love to know what other people think about it. I don't know if anybody else wants to chip in at this point. Can we make this a round table discussion, Russell?
You had a question, maybe you've got a comment.
Perhaps just relating to that point, I mean, people like John Wheeler seem to talk about observer-created reality, and you know, we somehow backwardly cause the universe to exist. But on the other hand, the moon, the solar system, the rest. So there's a bit of a paradox there. And I also wanted to ask, and whether there is, whether you see there an objective reality, if you like, before the measurements made, whether there's some kind of objective reality to that, which these is probably consistent with these theorems and Bell's theorem. What you can't have is something that's non-local, classically realist type of thing. But you know, yeah, okay, I'll ask that.
These are all very good questions, Rodney. I'm just concerned that we don't leave anybody behind, because you're using quite a lot of technical jargon there. And I know what it means, but I don't know whether everybody in the room knows what Rodney is talking about. I don't know if you want to moderate this, Russell, just to make sure that everybody's included in the discussion.
If you're able to give a 30-second interpretation of Rodney's question, and a 30-second answer, that would be perfect. That was a wonderful question.
So let me just pick up on one of the points that Rodney was making, which is called superposition of states. Paul Dirac, who did some of his most important work here in Cambridge, said that the unique thing about quantum theory is superposition, by which he meant that something can be in one state and another state at the same time in a way that bears no correspondence to our everyday experience. So don't try to make it correspond. It's as though an atom can be here and there at the same time. And so this is known as a superposition state. And Rodney's asking the question, is that real or not? And the simple answer is there is no consensus amongst those practicing in the field as to whether or not that is real.
So there is an asymmetry in time, in the sense that irreversible things happen, and therefore there is a difference between what has happened and what might happen in the future. I think the many worlds interpretation of quantum theory is crazy. And so I would define reality as what has happened. Because when an atom actually decays, before it decayed there was a probability, afterwards you know it actually happened. Welcome your views on that.
Well, does everybody follow the question? The answer is some people think like that. The Everettian interpretation of quantum theory is due to a person called Hugh Everett, who about a little over 50 years ago came up with a theory that appeared to resolve all these difficult problems, like the measurement problem that I alluded to earlier, in the following way, that he said that every time a measurement occurs or an event occurs, and that in itself is a huge question of what is an event, you get another universe spawned off, so that each possibility is encapsulated in another universe. And it is indeed the case that at the pure level of logic, if you accept this Everettian view, it does remove the measurement problem, but it removes it at a cost. It's cheap on explanations, it's very expensive on universes. And Oxford is a hotbed of Everettianism, so I have to be very careful disagreeing with it, or I get lynched when I go back to Oxford. But I think in summary one could say that many people practicing in the field find it logically watertight but profoundly unsatisfactory as an explanation. Let's leave the question of the asymmetry of time for another day.